Hi, thanks. So let's get started. All right, so thanks for the invitation to the very nice workshop. I really enjoyed the talks in the morning. Great posters, glad to be here. So I'm going to talk about adversarial or stochastic and in connection to linear bandits. So we'll see that linear bandits are surprising us again. Okay, so what is this talk about? So first of all, writing this book with Thor, who can be seen down there, very happy because we are about to finish the book. The book will be free and it's all about bandits. It's like 500 pages about bandits. These exercises and solutions to exercises and everything. And the PDF is going to be posted on the website. So going back to the talk, what is the talk about? It's an interesting word. Is it stochastic? Is it adversarial? We very often choose one of those because we are more comfortable working with them or for whatever other reasons. And I think it's good to make a step back and then investigate why you choose one over the other. What are the advantages, disadvantages of these choices? What are the consequences of the choices? And here I'm going to tell you two tales, which are kind of similar, slightly different. The case of finite arm bandits. How many people are familiar with finite arm bandits here? Okay. Good. And both for adversarial and stochastic and then linear bandits. All right, so let me start with this slide. Everyone knows this quote, but I think that we can't repeat it frequently enough. All models are wrong, but some are useful. So why this quote is relevant? Well, because we're just talking about modeling choices here. Whether you want to model the environment as stochastic or as an adversarial, it's your choice. You might think that, you might have some beliefs that the world is stochastic, but I'm here to tell you that the world is not really stochastic. It's just a modeling choice that we make. And it may work or may not work. And it is really worthwhile to investigate this a little bit. And then if you are a little bit worried about whether you're making too strong assumptions about the environment, you might end up saying that, okay, let's just assume that the world is adversarial, but an adversarial world is not a very welcoming place, so then there could be some price that you need to pay for that. And the question is there really a price? Is this a duality, or like how does it go? So in this talk, I'm going to, as already advertised, look into this problem in the context of bandits. And we start with stochastic finite arm bandits. So you have three machines. They have different payoff probabilities. You can pull the arms. And you can just compute the regret. Ian in the morning was arguing very eloquently that the regret is the right quantity to measure things with. So, right, so I guess I don't need to say more words about the stochastic case. So here the assumption is that the rewards are generated in a stochastic fashion from some distributions underlying the arms, maybe Bernoulli distributions, maybe other distributions, and independently of the past action. So if I choose an arm, then only the identity of the arm is going to determine what reward I see, and it's going to be stochastic. So that's the stochastic setting. Regret is just like, okay, how much could I have gained if I've only chosen the best arm all the time versus how much I gain altogether. And to summarize decades of research on a single slide, so by now, we by and large know what the heck is going on in the stochastic finite arm bandits. So we know that the worst case regret scales with square root number of arms times number of rounds. That's the best that you can get in a worst case sense. And we also know that asymptotically and even in finite time, the best that you can get is this logarithmic regret that scales inversely proportionally to the with the gap of how much you have to pay for choosing a suboptimal arm. So these are the results. There are lower bounds, upper bounds, by and large matching, and people are really nailing down this problem. And all right, this is great. It seems that we're making progress until you realize that, well, something like this might happen, like it shows maybe the rewards that you might observe if you keep pulling just one arm, and then you might see some deviations from the normal behavior, and then you might start worrying whether your algorithm is going to be ultra sensitive to these deviations and it's going to be thrown off the cliff, and then it just like lands and crashes, and things are bad. So does this matter? Is this, okay, so if you see this, then you might ask, okay, is this really a stochastic word? Maybe it's not. And of course, we do have an interesting alternative. And the interesting alternative is just this adversarial setting where maybe in one version of this, rewards, maybe just zeros and ones, are assigned to the arms and the given rounds ahead of time. So there is this table that is filled out in some way. Maybe the table is filled out after the environment looks at your code. So might worry about the worst case table given your algorithm. And then your algorithm goes and in every round has to pick one of the numbers by not seeing the others. And then those are the rewards that are received by the algorithm for that round. Okay, so this is the adversarial setting. It's been introduced a long time ago. And since we're not making any stochastic assumptions about how the table is generated, the entries in the table are generated, it seems that it's going to address the problem that we have, that the stochastic assumption might be too brittle. So the question is, okay, so if we go this way, what can we do? So this is just formalizing the problem. It's just introducing some notation. XTI is the table, and then AT is the action, and then you observe these rewards, and then you still have the regret. Well, you have to be a little bit more careful with the regret definition, because you can't just use the mean like according to a statistical sense, but you can go back and then compute the empirical mean across the rows of the table. And then you want to compete with the best row of the table. Okay, so that's the adversarial setting. And what we know is that this setting seems to be trumping the stochastic setting. So how do we know that? In computer science, we'll have these reductions. John is there. He was speaking a lot about that we should talk about reductions, and we should do more often reductions because we don't want to duplicate work. So if you can reduce one problem to another problem, then it's enough to solve the second problem, maybe. So can we reduce stochastic bandits to adversarial bandits? Yes, you can. So how do you do this? You start with a stochastic bandit, finite time bandit, and then you want to come up with an adversary environment. This is kind of trivial. You fix these distributions. You generate the table entries at random, uniformly at random. And then the question that you need to ask is whether the regret concept is the same, whether it reduces. And you will see that by and large it's kind of the same. I mean, you have to define now the maximum over the stochastically generated entries in the table, and those should be close to the true mean. So they are, lo and behold, they are really close to the true mean. So the additional price to suffer by reducing the stochastic problem to the adversarial problem is at most bounded by, without doing any, like designing any algorithms, that the additional price that you're going to pay is at most, I forgot to multiply, but at most square root n log kn, and then you can refine this analysis, and it turns out that you're not losing anything if you are making this adversarial assumption, or if you start working with adversarial bandits. Of course, you might worry about that. Maybe we are losing something because in the stochastic world, we had these instance-dependent regret bounds that scaled logarithmically, so you could adapt the individual instances in a near-optimal fashion. And then you might ask, like, is that still possible? So can you have an algorithm that works both in the adversarial and stochastic environments, and it gets the best of both worlds? Meaning that, of course, it has the worst case guarantees, and if it works in a stochastic environment, then somehow it detects quickly enough that it is working in a stochastic environment, and then it almost matches the lower bounds. And then by now, we kind of know that you can do this. So there's been a very nice long line of work that was addressing this question. So with that, let's switch to linear bandits, which is maybe a little bit more interesting. So what do I mean by linear bandits? So why do you care about linear bandits, first of all? So it's kind of the simplest setting where you are bringing some tools to deal with the complexity of a large world. Maybe you have a large number of actions, and because you have a large number of actions, and you know that in the worst case, your regret is going to scale with the square root of the number of actions. You are uncomfortable about this, and then you want to somehow maybe either make the environment nicer, or you want to change the goal a little bit. We'll see that there are these two ways of thinking about these linear bandits. So maybe you're going to put a restriction on the environment. That's what stochastic linear bandits are doing. And then in the adversarial setting, you kind of change the way you're thinking about the problem. You want to have a more modest goal of competing with not the best arm, but like just some, we'll see how it's done. Okay. So that's the idea. So how do we do this in a stochastic setting? So the simplest way to do it is that you have these k arms, and each arm has an underlying feature vector, which is given to you ahead of time. And then you make this assumption that the way the rewards are generated for the arms is by taking the inner product of the feature vector of an arm with an unknown parameter vector, and know the object of interest. In a way, it's like you can understand what's going on. So everything is d-dimensional here, and d is supposed to be, let's say, smaller than k. So you have a handful of features and maybe millions of arms, and you try to win this way. You need to learn about a lower dimensional object. And you can generalize this in different ways, sparsity and whatnot, but let's keep this simple. And the main results in the literature just tell you that, yes, you can have algorithms which generalize to this setting, and indeed you can replace the square root dependence on the number of arms with actual linear dependence on the dimensionality of the feature space. Okay. So let's look at the adversarial setting. The adversarial setting is very similar. It kind of copies the finite time adversarial setting. So the adversary is going to select a sequence of parameter vectors. These are theta of t. So instead of the rewards being generated at random, the adversary selects this sequence, and you change the criterion a little bit, right? So now you have to compete with the best average, so you want to compete with still the best arm, but with respect to the best, with respect to the average parameter vector in hindsight. And lo and behold, you can do it. You can design algorithms that are able to do this. It seems that kind of things are all right until you discover the case of the curious case of the unit ball. So here the number of actions is infinite, but we shouldn't be much bothered by that. So what is known for the unit ball is that for the stochastic linear bandits, and this is where things are getting a little bit more exciting and interesting, the regret is going to scale linearly with the dimension. So the lower bound and upper bound are the same. And for adversarial linear bandits, you can design an algorithm with a mirror descent where the regret scales with the square root of the dimension. So then you might be wondering about, like, didn't we say that the adversarial environment is just like harsher and bigger, and so like how come that the regret is actually smaller than the lower bound that you have for the stochastic environment? So this is kind of like a puzzling situation. At least when I first saw it, I was like, really? What is really going on? So this is kind of what the talk is about. So if you would try to do a reduction as before, and you would have this additional term, the additional term would need to be as large as the worst case regret. So that kind of just doesn't make, it's much larger than the regret for the adversarial setting, so it kind of doesn't make any sense. Or like something strange is going on. So pushing the ideas of reduction, you can actually push it, and the only thing that you need to do is that you have to augment the feature space and the parameter space by an additional dimension. So to emulate the stochastic linear bandit, one way to do it is to add an additional dimension both to your actions, and there the value of the new coordinate is going to be fixed to 1. It's like a bias term there. So that the figure kind of shows that maybe you have a 2D sphere, and then you have to kind of push the 2D sphere into 3D, and it becomes this 3D disk, which is offsetted from the origin. Okay, so that's what the action space transformation does. And then with that, you can push through the reduction. So how do you do that? Well, so the problem was that you have this stochastic noise, and somehow the noise should go into the parameter vector, because in the adversarial setting, it's the parameter vector. That's the only thing that you can play with. So how do you come up with that parameter vector? Well, you keep the fixed parameter vector for the stochastic setting, and then you amend it with this noise component. So you add this additional noise component. And with this, you have a reduction. So you can push through the math. The two regrets under this reduction are exactly equal. So if you can get an algorithm for this offsetted disk for the adversarial setting, then you can get an algorithm for the sphere in the 2D setting for the stochastic case. So that's a little bit weird, right? So what is really going on? So should we really be concerned or bothered by this? So for example, you might ask, okay, we have this mirror descent based algorithm that gives you this square root dn regret for the sphere. So what happens if you run this algorithm without any changes, without changing the learning rate? Then you will see that it's going to suffer actually a bigger regret than a stochastic algorithm would suffer. So it seems that in the stochastic environment, it kind of works, but if you're not prepared, if you're not trying to detect that you are living in an easier world, then the regret goes up. So maybe we shouldn't just think about stochastic problems as easier. They're just different, right? So I think that that's kind of the big lesson, at least for me, from looking at the unit ball. and throwing in this the features and the models that introduce dependencies between the arms. So if you have problems where there are dependencies between the arms, it's far from obvious whether the stochastic word is going to be an easier or a harder word. And you have to be careful with this. You might need to change the algorithm to actually get the worst case regret. And indeed, you can change this algorithm to actually match the worst case regret. That's available for the unit ball. But we don't have any results as of yet, so this is a nice open problem for everyone present to design algorithms that adaptively detect that they are in a stochastic world and are able to switch between, or not necessarily switch, but like hopefully in a very nice and graceful manner adapt to the qualities of the environment, let it be stochastic or adversarial. You might also think that it's a good idea to throw in adversarial framework if you have the unrealizable stochastic linear bandit setting. And in general, we don't know whether that's true or not, for the same reason as shown on the previous slide. But actually, on the unit ball, you can do the computation for this mirror descent-based algorithm, and it happens that it works. So it kind of gets this the best possible regret for this unrealizable setting, for the stochastic setting. So that's kind of cool, but again, like, we don't have a general answer to this question, so that's an interesting question. So what to conclude? So I didn't mention this, but this whole word of adversary and stochastic, of course, originates in the full information setting in online learning. People there kind of discovered slowly that a better way to think about machine learning is just thinking about individual sequences without making any assumptions about what losses where the losses are coming from. And you can push through all the analysis, and you can do this reduction from the adversarial case to the stochastic case. We see that in the bandits, in the finite time bandit case, it kind of works the same way. Like, you're not losing pretty much anything. I mean, like, you have to be careful and you have to design more clever algorithms if you want to really adapt to the niceties of the stochastic world. But by and large, at least in the worst case regret, you're not losing anything if you just apply your adversarial algorithm the way it is written in the textbook. It's going to match the worst case regret for the stochastic environment. Maybe it loses a log term, but okay. But in the linear bandit case, that is not the case. There you have to work, even just match the worst case regret. So I think that that's a little bit overlooked. So in conclusion, stochastic is not a subset of adversarial, and it's kind of an interesting word. Thank you.
I have one question. What are the implications of this work for non-bandit settings?
Okay, so I think that, so the reason to study linear bandits is because it is the simplest case where you somehow bring in generalization, you bring in function approximation. And I think that maybe the implication is that whenever you do this in more complicated settings, MDPs, let's say, I expect similar things to happen. Of course, in MDPs, the adversarial thinking is getting a little bit more complicated because if you're thinking about adversarial transitions, then things can get really hard very soon. But there are other ways to think about making things more robust by looking at adversarial settings. And I think that the very, very general message of this is that things are not so simple. So just because you throw in an like you switch to the adversarial thinking doesn't necessarily mean that if you're not careful, it doesn't necessarily mean that you are also covering the stochastic case.
So a lot of these results would be for the worst case setting, I believe. And so this stochastic can be just as hard as adversarial in the worst case. Is there some notion of across actual realistic problems you might see that still stochastic is less problematic than adversarial? Like, is this just an argument about worst case, or is it an argument about generally?
Thanks. Right, so for the finite embeddeds, we know kind of what is the best that you can expect to see, what is the best trick that you can expect to see for a given instance for across reasonable algorithms that kind of like match the minimax regret over a class of environments. So we have a notion of like instance optimality, and you wish to have algorithms which are near instance optima, so adapt to the individual instances in the stochastic setting, and that's what this best of both worlds line of work was trying to address in the finite time setting. And the situation is much more muddy in the linear setting. We know very little about these instance optimal bounds, finite time instance optimal bounds. How even to do that in the stochastic case, we don't know. And, but we should know it, and then eventually if you do, then maybe you want to design an algorithm which interpolates nicely between the adversarial and stochastic world, but it's really important that we try to push this adaptive. So maybe another way to put it is that, well, the adversarial, even within the adversarial literature, it's not just first case. Like people look at this adapting to this regularity, adapting to that regularity. So there's all kind of works there.
Any other questions? Let's thank the speaker one more time.